Somewhere around a year and a half ago in like September of 2020, I did some flow rate testing on the E3D hemera, just to find out how fast it can print. The method I used to do that was one that I borrowed mostly from Stefan at CNCKitchen. This is a method where you extrude a known amount of filament at a set flow rate and temperature, and you weigh what comes out. The difference between what comes out and what should have come out will tell you how much it under extruded. So for example, if 95% of the mass came out, you know it's 5% under extruded. It's a pretty good method, but it does have some limitations. Today though, I'm going to be testing a different hotend to try and find out the relationship between temperature and flow rate, how one impacts the other, and also try and find an ideal printing speed for this specific hotend. We'll get into that later. The reason I wanted to share this is because I came up with an entirely new test method to do it, and it provides an amazing amount of detail, and it kind of was so much information I almost had like an information overload looking at the results. So I think it's absolutely awesome. So hopefully you do too, and hopefully I can express quite how interesting and exciting I think this is. So let's get started. Today's video is sponsored by Ooze Nest. Ooze Nest have a broad range of popular, glamorous and engineering materials for 3D printing, including PETG, Glitz PLA, nylon, polycarbonate and many more. Plus an amazing selection of colours, probably the broadest range of ABS colours available on the market. All their spools are also made entirely of recyclable cardboard, so you can shop without the guilt of disposable plastic spools. If you're looking to stylize your Voron, rat rig or other 3D printer, check out their materials in the link in the video description. So as I mentioned on the previous method I used, that I borrowed, I think there are some limitations, which is fine. It's very easy to access and it's very easy to do, but I really wanted to see more. So some of the limitations that I found with it was that first, there's only one data point. So however much information you try and glean from it, at the end of the day, it's one piece of data. Secondly, you can only do your one data point after the test. Because you're weighing an amount of filament that came out, you can't do anything like in the middle to understand how it came out or the rate at which it came out. It's just whether it came out or whether it didn't. Number three is that my cheap scales do have quite a bit of error. So when we're only weighing very small masses, unless you get some really expensive high precision scales that are also very accurate, then your measurements can be a little bit wibbly wobbly. Number four is that the weighing method I think could be missing the point at the flow rate where it actually starts to make a difference. For example, when that flow is coming out, sometimes they look glossy, sometimes they look matte, sometimes they go really fat. And all of this I think is part of indicating where the limit of the performance is. And number five is that sitting in front of a printer weighing lots of things is not particularly healthy, I don't think, especially when you're printing things much hotter than they normally would be, just so you can test at a specific temperature. So with all of that in mind, I started to get to work on a new idea, a new way of testing hot ends and extrusion that I'd not seen before and I thought could be a really good idea. So, you know, bit of CAD, doing some design, writing some code just to see what works, getting a few parts in to see, you know, what's suitable, and I've come up with this. Say hello to Brute Forsyth, my extrusion testing rig. The way it works is that we have an extruder mounted directly to this very solid frame, and then beneath it we have a hot end mounted to a load cell. A load cell is basically a piece of metal with a strain gauge on it that measures how much it bends. So only very infinitesimally small amounts normally, and it's basically a way of measuring force. So with calibration, we can work out how much this is pushing down. It's quite an improvement, I think, so let's run some tests to see how everything works out. What I'm testing here is the Dragon hot end fitted with a brass 0.4mm nozzle, a 40 watt 24 volt heater cartridge, and an E3D thermistor. The actual test that we're going to be running is to extrude filament out of here through here for 15 seconds at a specific hot end temperature and flow rate. We're going to then vary the temperatures and vary the flow rates and plot all the things that we get. Obviously, once we've captured all that data, I've run through all of that information in Excel and made graphs and all this kind of stuff. So now you just get to see all the lovely results that I've made. This is where it gets really interesting. Oh, by the way, don't forget to subscribe if you want to see more cool stuff like this, because I think it's flipping amazing. Right, let's go look at some results. So for the results I'm going to look at, first we'll look at some stuff in detail, just so you have an idea of the kind of patterns and things that we're looking out for. And then we'll kind of generalize into kind of a big picture using averages and summary to try and find out the kind of specifics about performance of this specific hot end and nozzle combination. So this is the results for 220 degrees Celsius, and I've done 7 different flow rates here. So the dark blue line is probably the most obvious here. It's the one that's straight through the middle of the graph. Very high forces, lots of wobbling going on. So those peaks and troughs, like through the majority of the graph, this is where the drive gear was basically slipping on the filament. It was trying to push so hard and the teeth just couldn't grip hard enough, couldn't grip strong enough, and just basically ate the filament. But also the peak of those peaks is how much force can be applied. So if we read that off from the left-hand side, it's somewhere around 2.8 kilograms of force that those gears can apply. By the way, I know that the Stefan motor could be skipping, but I know it wasn't for any of these tests because I did actually sit with it, even though I said I wasn't going to. So next, right before all those peaks that we just talked about, we've got this additional peak that's somewhere near 4 kilograms. So if we were slipping at 2.8, how on earth did it reach 4? Is definitely interesting, but I'm not sure why. Next we have this flat part near the start, and this is actually repeated in the test below it as well. And that bit is pre-melted filament. So because of the way I had a bit of idle time before running the test, anything that was already in the nozzle can obviously pre-melt. So then when you start the test, you have an amount of filament that can just go pretty much straight out at a reasonably low force, but at the highest flow rate that it's trying to achieve. What's really cool is that knowing that we have time on this graph, we can actually work out with the flow rate and the time how much filament is in the hot end pre-melted, right? Because the amount of time that it's in that period where it's applying a consistent force, that's how much filament is in here. And then it peaks when it starts to go hard because it can't keep up with the flow rate. That's awesome. Anyway, next one. At the end of the test, we can see where obviously everything drops off because filament continues to come out of the nozzle, and that reduces the pressure on the nozzle. So for this test, I just turned the motor off, so you can see how it just gradually decreases. But if we added retraction in, that would immediately pull some filament back and reduce that spike very, very quickly. And obviously we could tune the amount of retraction, and it would probably, we need to test it, but probably change the rate or the amount of the pressure drop that you get, and then we could work out how quickly we can get to 0. We could actually use this to manipulate the motor rotation or back rotation to work out the quickest way to get to 0 pressure. In other words, you can use a graph and without any printing work out what your retraction settings could be. So we know that this highest flow rate is not going to be useful. Like there's skipping all over the place. The actual extrusion that came out was total garbage. So let's hide that line and we'll zoom in on some of the other bits so we can see them a little bit clearer. Right, relax, it's exciting. So this flat part at the beginning, this is what we talked about, this kind of pre-melted stuff. Why is there a spike just before it? So a couple of theories. One is because I disable the motor at the end of a test, so when it's at the start of the next one, it has to enable. Maybe that enabling causes that spike. Now normally you don't disable a motor during printing, so you wouldn't see that. But that's how I've tested it here. Then I think potentially it could be related to pressure buildup in the nozzle and a kind of stick-slip motion, so where you need a lot of force to get it moving, but then once it started moving, the amount of force reduces. Maybe it's something a bit like that. Another thing that you can start to see at this scale, now that we've zoomed in a little bit, is the continuous kind of peaks and troughs, the sort of rippling in the 60, 120 and 240 lines. I'm not really sure what that is. It might be to do with the kind of vertical artifacts thing. It might be something like a 602 looking issue, because those changes in force suggest that the flow rate is also kind of fluctuating as well, and that would make the lines maybe wider and narrower as it's printing. Again, the two highest flow rates, pretty sure that those are not going to be useful for identifying what this particular combination can do. So we're going to hide those and zoom in yet again. So let's talk about the blue line now. That's only half the length. The reason is, I don't know. It should have done 15 millimeters a minute for 3.75 millimeters, which is 15 seconds. For some reason, it only took 7.5 seconds. Why? Who knows? Must be some sort of minimum extrusion speed for some reason. The other things that we see in the blue and also in the orange test just above it is like this weird dip. Now, we'd looked at peaks and troughs in the very high flow rate graphs, and we can conclude that those were skipping of the teeth on the filament. But this is like almost nothing flow rate. Like the filament was basically falling out of the hot end. So why is it that we get this weird pit in the graph rather than just this nice smooth line? We can tell that it's not slipping because the dip is kind of slower. When it skips, it's kind of immediate like that. So the line just drops. Whereas this is kind of ooh, and then goes back up again. A little bit more testing, I think, needed to find out. But we'll see from the other tests later on, it does seem to be common with low flow rates. So what can we be sure of from this first kind of initial testing? Well, the faster we try to push filament, the more force is required. I think we all knew that, but now we actually have data. We can say how much force is needed to push a certain flow rate, rather than just, well, we probably need some more. We know exactly how much because we measured it. That is why this is interesting. So let's take a look at similar tests, but now we're going to put graphs for temperature. So this graph shows all the temperatures from 180 to 260 for a single flow rate of 60 millimeters a minute. That's the motion of the filament. I think I mentioned this before, rather than the printing speed. It's just how much of the filament is being fed through the extruder per minute. You can see for pretty much all the temperatures, like there's a really clear pattern. The flow rate is quite low, so there's no slipping. The gears didn't slide on the filament or anything. And the extrusion force is peaking at 900 grams and nothing really goes past that at all. But we can see still that that starting peak, although a little bit less sharp, is there for basically every single flow rate. It just always happens. The moment you start, it goes boo, and then down a little bit. Got to work out why. As you might have guessed, the lower temperatures require more force because the filament is more viscous, it's more closer to its solid state than it is to the liquid state. So it requires more force to push through tiny hole, but with obviously some diminishing returns with the higher the temperature gets. In the 250 and 260 degrees Celsius graph specifically, you can also again see these pressure drops that I talked about earlier, where the temperature is very good and the flow rate is very easy. So you seem to get these pressure drops. They're definitely not slipping. So that graph was a low flow rate. Now let's look at the kind of the same, but for a high flow rate. So in this case, 360 millimeters a minute. This one doesn't have a graph for 180 degrees Celsius because the force required to push 180 at that speed was just basically impossible. So there's no data. Again, we can easily see that starting peak. The moment you start extruding, it peaks and then goes into this little flat area. So in the first graph we looked at, we saw that flat area. We're like, well, this is the pre-molten filament that it can do easily before it goes into the state where it's having to work much harder to melt filament as it goes. And you can see that in every single graph here. Every single one peaks flat. And you know what I said as well about measuring how much flow is in there? You can see the length of all these areas is basically identical, which means at the same flow rate, the amount of time that we can push this pre-molten filament out is the same, which makes total sense. It's the same volume in here being pushed out, and it's always being pushed out at the same rate. At the 190 and 200, we can start to see teeth slipping. So at one moment, the gears just couldn't grip the filament, so they kind of slid, and the filament kind of shoots up a bit and the gears shoot down, and it's all just a mess, and it's definitely no good for any printing. So basically anything with that in, no good. But what we can see again is that we have peaks around the same area. So somewhere around the 2.5 to 3 kilo range, that's the maximum force that these teeth seem to be able to apply for PLA. Would probably change for different materials because they're different strength materials. So now that you know what's going on, what kind of things we're looking for and what kind of patterns and things we get out of this, let's take a look at a kind of summary graph so you can see all the data together in a summarized format so we can actually draw some conclusions. So this graph plots force against the temperature, and you can see pretty clearly from the graph how increasing temperature reduces the force required. Hopefully that should be fairly obvious as well. But now, because we have the data, we know how much difference, rather than just it changes. Not only that, but we can actually see the increasing force from one to the next. So if we look at 220 degrees Celsius, for example, that requires around 450 grams of force to extrude at 120 millimeters a minute. You can see from this point here. But if you bump that to 240 millimeters a minute, the force required jumps to around 800 grams. Again, we're totally quantifying every single part of this extrusion system. Looking at the graph as a whole, the position that lines start and stop is not random either. Now, it looks like I've just cut the top off, but literally no data on this graph went above 3,100 grams. And again, it's not because I cut it off, it's because the gears were simply not able to grip the filament any more than that. If you try to push with more than that force, it slips. We know that. So this kind of shows that this is not just testing the hot end, even though it's the hot end that's mounted, it's testing the extruder as well, because we can see how much it can force, how much force it can apply, how much it can force. What we can also see is that the blue and orange for 15 and 30 millimeters a minute, they do kind of interact, they kind of intersect quite a bit on this graph. They're overlapping each other, they're kind of changing around. And I don't think this is because it's an error, I think because it's more that the temperature and flow rates were below any of the limits fairly significantly. So adding that extra temperature, extra flow rate didn't really make much of a difference. So the results just kind of intertwine, and it's only error that's kind of making any changes there. One other thing that we can actually do with this data is start to visualize how good the flow is. And we can do that using something called standard deviation, or determining how far the force values that are being applied vary from the average value. So if the average is here and the values are shooting way up and way below, the standard deviation will be really large. If they're very consistent and very close to the average, then the standard deviation is very low. So we can use that to understand if it's peaking and troughing, that's going to be a bad flow and would have high standard deviation. If it's a good flow, low standard deviation. So by calculating that, we get this graph. Now we need to experimentally determine how much standard deviation is good or bad. Well, I've made a guess of 85 grams. And so at 85 grams, we can draw a line onto this graph. And from that, we can determine that anything below it is okay, it's worth doing. Anything above it is not worth doing, it's going to be garbage. Who'd have thought, right, pushing some molten filament through a hot end using old brute force scythe here, what an amazing piece of kit. I really was not expecting, I thought it would be pretty good, which is obviously why I did it in the first place. But this level of detail that we found is just, it's crazy. The whole time trying to make this video, I'm like, but I could test this, and then this, and I want to do that, and that, and that, and that. And we could do like a whole array of things, and we can work out, like, oh, it'd be so good. There's so much testing you can do with this one machine. Oh, it's insane. Anyway, let's try and find some conclusions. So, from studying the pressure drops, slipping gears, consistency of force, my estimation from this data so far is that the ideal flow rate for best quality from this specific hot end is around 120 millimeters a minute at 220 degrees Celsius. Now, it's not particularly fast. It equates to around 4.8 cubic millimeters a second, or somewhere in the region of 67 millimeters per second at 0.4 millimeter line width and 0.2 millimeter layer height. That's not hugely fast, but this is the standard flow, remember, not the high flow variant. So we wouldn't necessarily expect something enormous, but I would have probably expected something more than 4.8. I think the reason we get something quite low is because we're evaluating with much more insight the quality of the flow. So with this method, we can see something before it happens rather than just pushing into it and going, oh, that looks okay. It might look okay on the outside, but with this, we can tell from the force data that something is definitely different on the inside because it requires more force to happen. So with this, I would expect maybe a lot of flow rate results to end up a little bit lower than normal, but I also suspect that we will get more attractive prints as a result. So in terms of conclusions on the actual brute force scythe test rig then, there's definitely a lot we can do with it. For example, we can print different patterns. So instead of the kind of on for a set amount of time and then off kind of pattern, we could do steps. So on for a bit, and then up a bit, and then up and up and up. We could do just a gradual increase. We could do just a long flat line. Does it drop off over time? Could that be a good way to test whether heater cartridges are sufficient, for example? And I think what's important from that point of view is that the nozzle hot end performance is no longer just about peak flow rate. It's not just how fast you can push. Because as this shows, there's not one set value. Like there's not one thing that goes, oh yeah, that's the maximum. Right there, we can see it. It's, well, you can push a little bit faster, you can push a little bit lower, and it'll have this effect. It's not just, boom, that's the one value. So, you've really got to let me know, is this something that you find interesting? It's certainly something that I find interesting. I've absolutely loved working with this, doing all those different things, finding all this intricate detail. It's so good. If it's something that you want to see more of, please let me know. So that's it from me today. Thank you very much for watching, and I'll see you in the next one. Brute force.